Our today's speaker is Robijn Bruinsma. Robijn is famous for a number of things that he did in soft matter physics and in biological physics. He is also famous for the fact that although he is really professor in UCLA, but I'm sure he will tell you that he really is a Dutch farmer.
Okay.
Be prepared. He is Dutch farmer. Be prepared, he will tell you so. That's my prediction. So, Robijn, please.
Okay, thank you, Shura. I've just come to the end of a wonderful stay here in NYU for a month. It has been a fantastic experience interacting with you all, and I'll go back to the West Coast, comforted perhaps by the fact that you have a coming winter and we don't. So apart from that, I want to thank you all for making this such a delightful experience for me. So my talk today will be a little bit unusual. I want to talk about a concept, and not a concept I proposed, but a concept proposed by somebody else, and then another person extended that concept. And that's what I want to talk about, sort of the history of an idea. And the idea starts with this picture. It looks like something which belongs in the Museum of Modern Art. It doesn't. It's actually, I think Paul recognizes it. It's a liquid crystal. So it's a nematic liquid crystal. So it is distinguished from ordinary liquids because it's a fluid with direction. I have a very nice. It is a fluid with direction. So this picture is taken between polarizers, polarizer and an analyzer. So in essence, what you see here is a map of the directions. So it is a fluid with a local direction, and in some points it will point along the analyzer, and in other cases perpendicular, and depending on the polarization of the light and its relation to the direction, the light may or may not get through. So you see here a pattern, this beautiful abstract pattern, which actually is a map of the direction. So this is an example, this fluid, this nematic, of an orientational phase transition. Okay, so that's the concept I'm going to talk about. I'll spend a few transparencies, a few slides to tell you about it, and then how people have stretched this concept by applying it into a completely different area where it never was designed to work. So it's about the benefits and the risks of taking ideas from one area and bringing it into another area. So first let's talk a little bit about nematic liquid crystals. And if you have a textbook on nematic liquid crystals, you almost surely will see this picture. This represents organic molecules, to the horror of organic chemists, but it is an organic molecule, and we're not distinguishing the two ends, or you might say just 50-50. And there is an average direction, and that is the nematic director, which we represent by a double-headed unit vector because it doesn't matter whether we have it down or up, it's the same structure. So this is nothing else than the polarization axis. If you would write down the dielectric matrix, then this is it's a uniaxial structure, and this represents the direction if you have a birefringent material. So this is in a way a picture of the optical structure which you saw before on a very small scale. If you go to larger length scale, then this double-headed vector will vary across space, and you get these beautiful textures which I showed you a moment ago. Okay, now this is pretty intuitive. If you now go on reading your textbook about nematics, you will next see that you can measure the degree of order. This is the direction of the order, but you can also say how much order there is, and this is how it's calculated. 3 cosine squared theta minus 1 over 2. So what does it mean? So z, if I take the z-axis here along the nematic director, and theta is an angle, then what this instructs me to do, or which instructs the experimentalist to do, is calculate the probability of one of these molecules to have an orientation along this direction, and then average over all possible orientations. So you have to basically find the fraction of molecules pointing along a certain direction, and you do an average. Okay, now if it's completely isotropic, then the average of cosine squared theta is a third, and it's 0. If it's completely oriented, then theta would be 0, and you get 1. So it is a reasonable indicator of the amount of order. S equals 1 is fully ordered, S equals 0 is fully disordered. Now, experimentalists can measure the degree of order with a variety of ways, and it's possible to change this, for example, by changing the temperature. Nematics for which that happens are called thermotropic nematics. Incidentally, this is the same material you might see in your wristwatch as a display. So if you measure the degree of orientational order, or the amplitude, as a function of temperature, then at high temperature it's 0, just all directions are equally represented. It's an isotropic fluid, and then you cool it, and you go across a jump, and then this degree of orientational order saturates to 1. And this is typical of a first-order transition. So at this point, the isotropic fluid and nematic coexist. So it's a well-behaved first-order phase transition. By the way, please ask questions. I'm very used to it. So if I'm going too fast or whatever, just let me know. You look worried. No. Good. So we have here a first-order phase transition. Now, the concept I want to talk about is this. Why this expression? You can think of tons of expressions which go from 0 to 1. You go from an isotropic to an oriented state. So if you ask a theorist, and I did that when I was a graduate student, where does this come from, this 3 cosine squared theta minus 1? Then the answer is, it is a Legendre polynomial. Okay. So it is a Legendre polynomial, and that happens to be 3x squared minus 1 over 2. Okay. So why does that help? It didn't help me at all when I was first told that this is a Legendre polynomial. Where does it come from? Who dreamed that up? Okay. It's based on a theorem. So this is a mathematical theorem. We're not going to talk about mathematics, but yet there is a particular mathematical object which is going to play a big role in my talk. So here is the theorem. Any well-behaved function defined on the surface of a sphere can be decomposed as a superposition of spherical harmonics. Now, if you've had a class in electrostatics or in quantum mechanics, you've learned to hate and fear spherical harmonics. They are very common things which you have to do for your problem sets. And that's where the Legendre polynomials turn up. Here's the one we just talked about was L equals 0 and M equals, L equals 2 and M equals 0. But in general, for every L and for every M, there is a value. Now, this function, the spherical harmonic, you probably recognize from, let's say, quantum mechanics. And there you remember that this index M, which is the azimuthal quantum number, ranges from minus L to plus L. So M is minus L plus 1, up to equals to L. So it has 2 arguments, the same polar angle we talked about before, and the azimuthal angle phi. And here you see the quantum number M, and here's the quantum number L. So this is an abstract theorem. It's basically Fourier transformation. If you have a function which depends on time, or a function depends on space, and it's well behaved, you know you can decompose it into waves, e to the I kx or e to the I omega t. This is the same story, but on the surface of a sphere. So how does that apply to orientational transition? So we take an experimentalist viewpoint, and we suppose that an experimentalist measured for us the density of molecules in a liquid crystal oriented along omega. Just like I told you before, you take a certain solid angle and you measure the fraction of molecules which are along that direction, and you get some function of theta and phi in general. For a nematic, only a function of theta, but it doesn't have to be like that. And you then decompose that in spherical harmonics, meaning that you can write this measured function as an expansion in spherical harmonics. L runs from 0 to infinity, and for every given L, M runs from minus L to plus L, and these are the expansion coefficients. If we were doing Fourier transformation, these would be just the Fourier coefficients. So it's exactly the same as Fourier transform. And it is these expansion coefficients which are going to be the heroes or the villains of the story. A little historical note, the spherical harmonics were invented by Laplace in 1782 as the solution of the Laplace equation on the surface of a sphere. So if you work with his Laplace operator on a spherical harmonic, then it doesn't depend on m, it's an eigenfunction with eigenvalue L times L plus 1 over R squared, where R is the radius of the sphere. So we're going to use that later. I don't know if you knew this theorem that you can expand any function on the surface of a sphere in spherical harmonics. We need to go back to liquid crystals. So this is the mathematical machinery, and it doesn't yet tell me why it is one particular Legendre poly. Yeah,
how do you
please.
measure the density in a specific angle? How do you measure the density there?
How do I measure this rho of omega?
Yeah.
An experimentalist? Well, in principle, with polarizer and analyzer, I assume, you just look at the polarizer and your analyzer and you find if the system is perfectly ordered, it's thermally fluctuating, and then you rotate it and you see how the intensity decays as a function of angle, theta and omega. But I'm not an experimentalist, and I'm sure that there are smarter ways of doing it. In practice, you do it with Monte Carlo simulation. You just model little rods, and you simulate them, and you find a fraction of your rod-like molecules which are pointing along a certain direction. So this is the measured quantity, and this is the expansion, and this is what you extract from such an expansion. That make sense?
Yep. Thanks.
Good. Okay, so let's assume that we have measured it. And here is L equals 2, M equals 0. This is a nematic crystal, only one. For your pleasure, here I show the spherical harmonics for L equals 2 and M equals 1, and L equals 2 and M equals 2. So now, you are told that you only need this one. If you go to the numerical simulator and ask him, can you measure this and expand this? Yes, they can do that. And do you only see L equals 2? They start to laugh at you. Of course not. Like any Fourier expansion, it's a whole bunch of terms. So there's actually some why do we insist that we only need to worry about these ones if in actuality this distribution has higher harmonics? So why is it that we only need to worry about L equals 2 and M equals 0, this zeroth order L equals 2 Legendre polynomial, and can we compute the QLM? Good. So now we come to the concept. I started with you with orientational transitions, and here is the person who developed the concept. I'm not going to use his words, but the way it has been reformulated by people since then. The person is Lev Landau, and the concept comes from the Landau theory of phase transitions. And here it is. I'm going to tell you just a set of rules. And you can have many talks where these rules come from, but Landau developed a set of rules for this type of transitions, phase transitions, which have been proven to be very effective. So I'm only going to show you as kind of Mayan rules for computation. This is just a set of computational rules. We're not going to worry about it. The first thing what Landau said is you need to construct a variational free energy in terms of these coefficients, these QLM, which you didn't know. And you can minimize this with respect to these internal parameters QLM because of the second law of thermodynamics, which says that in terms of any internal parameter which can be freely varied, then at least at fixed volume and temperature, you have to minimize the variation free energy. So he told us to focus on such a quantity. Where does it come from? He said, well, you need to take, if this quantity is to go to 0 or nearly to 0, as it more or less does for a nematic liquid crystal, there's still this little jump. He said, expand this as a Taylor series. So linear, quadratic, cubic, quartic. So you have tons and tons and tons of term, right? Because for every case, you have to have all of the L's and M's. He didn't say this, by the way, because he didn't work on orientational transitions. This is how it was reinterpreted later. Here's the third rule. So this is just rules. So if you do this Taylor expansion of this variational free energy for these coefficients, which an experimentalist can measure, then the way to do it is that if you are in nth order in QLM, then you need to collect terms. The nth order term of the expansion must combine to form invariant polynomials. So that sounds like an abstract idea. under the symmetry operations of the isotropic state. Here is how it's formulated, and it sounds abstract, but basically think of, suppose that something is isotropic, and you have polynomials in x, y, and z, and you want it to be rotationally invariant, then this is an isotropic combination for the second order term. That makes sense? And you have to do the same thing for the QLM. And there is a whole branch of mathematics which does nothing else than calculating invariant polynomials. It's an area of mathematics, so you can just take my word for it that this can be done with complete rigor. You can construct to any particular order, you can construct these invariant polynomials. So with these three rules from Landau, I have a way of thinking about orientational phase transitions without doing any complicated calculation. I don't have to worry about things happening at the molecular level. Well, we'll see that is a little bit questionable because we still have to think about which L and M's are involved. But anyway, here we are, and I want to practice it with you. So we start with the very simplest case, L equals 0 and M equals 0. So for simplicity, I'm going to call that rho, because I don't want to keep on having all of these subscripts. So the first step of Landau is expanded in a Taylor expansion. The linear term it turns out it drops out because the integral of the density is a fixed quantity, it's a number of molecules. So we start with the quadratic term, cubic term, quartic term, etc., etc. And what we're going to do now is assume that this quantity changes from a positive value and we reduce it towards 0 or a negative value. So this is a third order polynomial. On purpose I take it negative, so there is a typical third order polynomial. And as you make R smaller, so R1 is large, then it looks like this. And Landau tells us that you have to minimize over there because you have the lowest value. There's a metastable minimum over here. So at this point, at this temperature or this value for R, R1, the minimum state is at rho equals 0. Then as you reduce R, this term becomes less positive. So the cubic term becomes more effective and eventually becomes negative. So you see that the special point here, there are two minima which are degenerate, and that's the point of phase coexistence. So you get exactly the kind of plot I talked to you about before. The density is 0 for higher temperatures, then there's a first order jump, and then it saturates. In fact, this is nothing else than a liquid gas transition. Just in a strange way, this is what it is. And if you do the same thing for an L equals 2, M equals 0 transition, it's exactly the same. Nothing changes. So Landau tells us, why is this a first order transition? Because there is a cubic term in the expansion. So that's Landau's rule, and it works. So L equals M equals 0 is easy. L equals 2, M equals 0 is easy. It predicts a first order transition. So now we're going to go to the big league. General L and M. So here is the horrible expression. It's exactly the same idea. You construct the quadratic invariant, the cubic invariant, and the quartic invariant. Constructed out of these QLM, and this comes out of pure math, these invariants. I mentioned to you there are strict ways how to construct it. This is like R squared equals X squared plus Y squared plus Z squared. This is a little harder, and this is a lot harder. This was written down by one of you visitors here, Paul Steinhardt. This was not written down by Landau. This expression comes from a paper from 1983 who worked on a special kind of liquid crystal. So this is the direct generalization of what I showed you before, quadratic, cubic, and quartic. You have the same R, W, and U term which we had before. Does anybody recognize this symbol? LLL, M1, M2, M3, numerical terms here. Anybody recognize it? Think of quantum mechanics? Well,
3J.
The 3J symbols. This is very typical. Very few people below the age of 40 seem to recognize the 3J symbols. Yep.
Guilty.
Sorry?
I'm guilty, yes.
Yeah, so it means that you had a serious class in quantum mechanics for additional. What?
Right here in this building.
Okay, I will not comment on this. So, apparently 3J symbols, they were invented by Wigner to talk about additional spherical harmonics. And they reappear here for essentially the same reason, to construct an isotropic term. Marko Jaric, a brilliant postdoc in Harvard who died tragically, was the one who wrote down all the quartic invariants. Okay, so this is it. In principle, it's more math because you have 2l+1 parameters, but you know, with computers these days, not a big deal. Now we come to the fourth rule of Landau. He says you only need to worry about 1l. And that is where this L equals 2, M equals 0 comes from. You have to worry about only one. Which one? Well, the one with the lowest R sub L. Because if you lower the temperature, it's the smallest one which first goes unstable. As soon as this one changes sign, it's unstable. In fact, even while it's positive, it becomes unstable if you have this cubic term. So you only need to worry about the lowest R sub L. That doesn't mean that there are no higher L's, but they're kind of slave. If you have terms coupling the different L's, then this primary order parameter will drive all the other ones. Call it entrainment or secondary order parameters. So that's the idea, and it works beautifully for liquid crystals. If you find this a little bit too hard going, you can do it easier by writing down a local density functional, f of rho squared, rho cubed, rho to the fourth, and then just sticking in this over here, and you'll get exactly that same expression. But this is how you do it formally. So we have machinery available to construct a free energy without doing anything complicated. The only thing we need to find out what is the lowest R sub L, and maybe you need a computer for that, or maybe InSight or an experimentalist tells you we are dominated by this particular L. Once you have it, everything is done. You know the phase transition. Good. So that's the idea. This machinery was applied to all kinds of cases. You have biaxial nematics, which is L equals 2, M equals 0 plus or minus 2 by Mr. Freiser. They were only discovered somewhere in 2004 as bent core mesogens, if I think that they are. Cholesteric and blue phases. This is a cholesteric phase. Look how beautiful it is. This is a blue phase, which is blue. They have a plus or minus 1. That's the signature, this plus or minus 1, that chirality plays a role for these. That was done by Hornreich and Strickmann. A little later, Nelson and Toner came up with cubatic liquid crystals with L equals 4. It's only been seen on the computer so far. And then the paper I already referred to you, Steinhardt, Nelson, and Ronchetti introduced icosahedral liquid crystals as a possible form of glasses, which tend to form icosahedral structures. I don't know if they've ever been seen. So at any rate, you could go on, but by the middle 80s, people had enough of it. So L equals 6 looked like it was sufficient, right? So this is the concept. Here, by the way, you see the L equals 6 structure you can make to get an icosahedron. I'll come back to that. So now we're going to change gear. This is the concept. These are the rules, and it's well developed, and it's a part which you can book in Chaikin and Lubensky, I think. Will be well discussed over there. Good. So now we're going to stretch this. And the stretching of the concept is to apply it in an area where it has no right to work. That is the assembly of viruses. So I'm going to shift gear. I'm going to talk about viruses for a while. I was told that this is bound to happen and that the quality of the view will become less, but I don't see any problem, sure, so it seems to work. Here you see a cryo-electron microscopy image of a small virus. This is for the same virus an X-ray diffraction image. So I'll explain it to you. The diameter is about 20 nanometers. And the 5, 2, and 3 refers to symmetry operations. So there's a 5-fold symmetry operation here, 3-fold here, 2-fold there, and they correspond to the symmetry operation of an icosahedron. This is 5-fold. The center of each of these 20 phases is 3-fold, and at the midpoint of these edges it's 2-fold. So many small spherical viruses have icosahedral symmetry. Here you see a more intimate picture. Red here is protein and green is RNA. And it's composed of 180 identical capsid proteins. This is the genome. It's an RNA molecule with 3 to 4 genes, typically for these small viruses. And this outer shell prevents the damage, or it prevents access to hostile enzymes, it prevents the RNA molecule to be digested by enzymes from your immune system, for example. So this is the package, proteins on the outside and RNA on the inside. And I'm going to talk about in vitro self-assembly. You might not know it, but you can make viruses in test tubes. In fact, the word self-assembly was invented for viruses, believe it or not, in the 50s. In the 50s, people for the first time were able to cook up a virus in a test tube. And the way that goes is that you take a test tube, you put in the RNA molecule, you put in the protein, you shake it, you do a dance, and you do something that experimentalists do, and out pop infectious viruses. So, but I'm going to talk to you about a way of assembling a virus which is perfectly controlled. It's work which was done in UCLA by my colleagues Nobler and Gelbart. So here we start. So in the solution I begin with viral RNA molecule. This is how they look like in electron microscopy. They look like kind of branched polymers, and they have a variety of structures. They are highly charged, about -3000, and the size is comparable to that of the virus. It's a bit bigger. This is 30 nanometers. So this is roughly drawn to scale. So you need to squeeze it somewhat to get it inside. These walls are thick, so you actually have to squeeze it a lot if you want to assemble it. So assembling a virus means taking this RNA molecule and somehow getting it on the inside here. You may have heard of these motors in DNA. It has nothing to do with it. In RNA, there are no motors packaging. There's no packaging motor going on. It's pure self-assembly. The reason why it has this strange structure is because a single-stranded RNA molecule corresponds of the 4 bases of RNA, and they can pair. So if you have a long stretch, then you can form all kind of hairpins and branch points, so you get a kind of complicated branch molecule. This was produced by a computer program called Vienna, and it sort of agrees, except there are very many secondary structures for the same primary structure. So your problem is then to compact this into a dense structure. It was quite compactified, you remember? And that's done by the capsid protein. So the next step in the assembly process is that the experimentalist adds the capsid proteins. And you have to do that very carefully, because you don't want to get a lot of aggregation which is not out of control. So this picture shows the capsid proteins. In a physicist way, this is one part and this is another part. Plus here means positive charge, negative means negative charge. So it's dipolar. There's a lot of negative charge here and positive charge there. They are amphiphilic, meaning that part of them likes to be in water, namely this part and this part, and part of them is hydrophobic, which is oily. So they tend to stick together. So capsid proteins have this unusual capability to form layers. Typical proteins don't do it. They go in solution or in membranes. Capsid proteins are special by forming layers. So the idea is that by hiding these red regions here, you get a kind of closed shell structure. Is that sort of reasonable? Okay. So you get empty structures if you do that. So the trick is you want to get RNA inside. So by the way, I should have mentioned, sorry, the hydrophobic attraction here competes with electrostatic repulsion. So the negative charges here repel the negative charges here, and the same for the positive charges. So it's a tug of war between repulsion and attraction. So we actually can alter that by changing the salinity or the acidity of the surrounding solution. You can make the balance go in one way or the other, but under physiological conditions, they don't assemble. You can make non-physiological conditions to get empty capsid, but not under physiological conditions. To cause it to assemble, you need the RNA. So here's the RNA drawn as a cartoon. Here are the negative charges. Here are the side branches. The side branches neutralize these charges. And by neutralizing these charges, you make it easier for these proteins to come together. So the RNA is actually triggering the assembly. The RNA neutralizes charges and makes it easier for them to get together. So that's the basic principle. The positive tail charges of the capsid protein, this is kind of very flexible, self-associates with the viral RNA, and the charge neutralization drives a compact form of the RNA called the RNA condensed phase. So it's mutual. The RNA causes the aggregation of the proteins causes aggregation of the RNA because the negative charge of the RNA is reduced by these tails. Now, the experimentalist can change this balance with acidity. The reason is that these negative charges depend on the degree of acidity. It turns out that if you increase the acidity, then you reduce the negative charge and you favor the hydrophobic attraction. So an experimentalist has a knob. He can turn on the assembly and he can turn off can turn off the assembly. So the self-assembly is a completely controlled process, and here you see an example, the cowpea chlorotic model virus. So on the left is just RNA. This is the RNA molecule. This is what you actually see, and this is the reconstruction. That's pure RNA. The next step is we add the capsid protein with low acidity, meaning that they don't attract each other. They still want to go to the protein. You see that it already begins to condense the structure because you've neutralized some of the RNA charge, so the RNA begins to shrink. Next step is you increase the acidity. That means that you reduce the electrostatic interaction and thereby strengthen the effect of the hydrophobic attraction, and you form an assembled structure which is an infectious virus. It's actually stages. Initially you form a structure which is not yet infectious, where you can send in RNases to gobble the RNA up, but eventually you form the pure virus. So the picture you get from this is that you have over here you have a sort of disordered protein RNA condensate. Increasing the acidity produces the assembled virus. This brings also, yeah.
Do you do that with any RNA, or does that has to be the RNA specifically for that virus?
It so happened that for CZMV, these were specifically done with not CZMV RNA because they were studying the generic mechanism. So for CZMV, you can do it with any RNA. So the RNA has little sequences called recognition sequences, which kind of make it recognize the proteins. So there is a selection process going on. But here, the emphasis of Gelbart and Nobler was specifically looking at the case of RNA which didn't recognize it. So it was a pure self-assembly problem. Good. So this is the picture you get, and for a soft matter physicist, it looks quite familiar. In soft matter physics, you often look at microemulsions where you have an oil droplet in water covered by surfactant molecules. In fact, these proteins look a little bit like surfactant molecules. But the strange thing is that in this case, it is these molecules, these proteins, which cause the condensation. That is strange, right? So you have here like oil and water, maybe RNA is soluble in water, so this is kind of fakery. It's not really that this is poor solvent, but it does want to condense because of the tails. And because it wants to condense, you form this layer, and it looks a lot like a sophisticated form of a microemulsion. And it is nicely, you might remember the negative charge out there that prevents these viruses from assembling because they're charged. So that's the transition I want to talk about. There are other experiments going on which I know less about. Fluorescent thermal shift assay, you look whether proteins on the same virus, you can check whether a protein is interacting with RNA or not, doing this fluorescence thermal shift. And in France, that gave a first order transition. But a very promising experimental technique has been developed by Vinny Manoharan in Harvard. Harvard sees viruses in new light, where you do microreology. You have a narrow tube, you flow the proteins and the RNA in on one side, and then by shifting your microscope up and down this tube, you can find different stages of assembly, and by doing fluorescent correlation spectroscopy, you can actually get the size of the structure. He got beautiful structures, and I invite you to have him out for a talk. Yes, sorry?
I was just wondering, is the population of main viruses monodispersed, or
If the viruses are monodispersed, 180 proteins, no more.
also in this in vitro?
That's right. They are infectious. You can test it because you take, this is a plant virus, you're not allowed to work with animal viruses. Take a plant virus, you can put it on the cowpea, and it will start an infection. So you can really make infectious viruses, but it's also possible to make polio. in test tube.
So I was just wondering if by this method, if you get like a narrow distribution, or is the number of particles always identical of the
Is the
building
size? You mean, which one? Do you mean?
Of the capsid, on the previous slide.
Okay, so the assembled capsid is supposedly to have one size only, 180 proteins, no more, no less. But a partial assembled structure can have a variety of sizes. And if you do electrophoresis, you'll see a broad band. So as you change, for instance, the concentration or the acidity, you see a broad band which is narrowing and narrowing when you get only the complete virus left. The RNA is a broad band because it doesn't have a unique structure in the electrophoresis experiment. Okay? Good. So this is, I'm talking outside my area of expertise, but I only wanted to show to you what is the experimental state. So back to my problem about concepts. Can we apply the Landau theory of orientational phase transitions to this problem? The idea comes from Vladimir Lorman and Sergei Rochal, and it was proposed in 2008. It was based on the fact that they noticed that a number of viruses, and this is an example, the K9 parvovirus, which infects dogs, and parvos means small, it's a small virus, 20 nanometer diameter, could be described reasonably well by a set of spherical harmonics. You remember spherical harmonics we talked about before? These are the expansion coefficients. We'll talk about where they come from. This is an icosahedral structure. So L equals 15 here. L equals 15 and M runs from minus 15 to plus 15. And they said this looks a lot like that. Here you see 1, 2, 3, 4, 5 maxima. 1, 2, 3, 4, 5 maxima. Interspersed by 1, 2, 3, 4, 5 minima. Here there's 5 holes. And they, in their paper, had a catalog of structures where they compared viral shapes with icosahedral spherical harmonics. And they said, this is crying out for a Landau theory. For the smallest viruses, their theory gives, they always want to use L equals 15. So now we're going to talk about, is this a sensible idea or not? This would make sense. Can you take the Landau theory for liquid crystals and can it say anything about the virus? And there are lots of skeptical questions. I mean, what phase transition? Landau's theory was for a phase transition. That's not a phase transition here. We just have this tiny 20 nanometer diameter structure forming in a test tube. Where does this L equals 15 come from? I can see that it looks right. It looks like the right structure. But why L equals 15 and what are these Q15M? What are the expansion coefficients? So first let me talk about whether or not there is a phase transition. Let's say we look at a simpler problem where we take clusters of spherical atoms, FCC, HCP, icosahedral structure. We can take all sorts of clusters, and I'm certainly allowed in each case to expand it in a complete set of spherical harmonics. In each case I can take the center and I can get the density along different directions for this very small object. Next, I can say these QLMs are now going to become thermally fluctuating variables. I have thermal fluctuation from FCC to HCP to icosahedral. Why not? And I can state that this has to obey the Boltzmann distribution with some energy which depends on the QLM. For a given set of QLM, I will get a given set of given structure. And the idea is now use the Landau functional for that. Just plug it in here. So this H is L Landau. That's the idea. I don't know whether it's sensible, but actually people do this in chemistry. It's something called local density theory for the electrons. It may or may not be right. If you can apply the Landau rules to construct this object, and then you can see if it works to predict the probability distribution for the expansion coefficient in this density. It's an idea, but it is not crazy. They're not saying that there's a phase transition. There isn't. They're only saying that I can use this Landau functional in there and say something about the probability distribution. So the idea that we do this for a phase transition is not crazy. It's a sensible idea. It may not be right, but it is not mathematically inconsistent. So the next question is, how do you justify using L equals 15? Well, it has to do with chirality. Capsid proteins are made of amino acids, and amino acids are chiral molecules. You have left-handed and right-handed molecules. All natural amino acids are, no, most natural amino acids are left-handed, certainly the ones in your body, apart from some of your bacteria, and the capsid proteins are all left-handed, so they're chiral structures. Now, that means that the capsid proteins don't have inversion as a symmetry. If you look at the spherical harmonics, the even spherical harmonics are all even under inversion. The odd spherical harmonics are odd under inversion. So, Rochal and Lorman said, if we're going to play this game, you have to exclude the even L spherical harmonics because it's a chiral structure. Okay. So that's simple, and it turns out that for a given L, you can find a unique combination which has the symmetry of an icosahedron. So the QLM are not just random quantities. They were actually, this concept was introduced by Felix Klein in 1884 in a beautiful mathematical study of higher order polynomials. There he introduced this idea that there are these combination of spherical harmonics which have the symmetry of an icosahedron. And it's only true for certain L. For the even L, 6, 10, 12, 16s form icosahedra. Here is 6 and 10. And these are all even under inversion, so we have to throw them away. For odd L, the lowest L is 15, then 21, 25, 27. So L equals 15 is the lowest odd L icosahedral spherical harmonics introduced by Felix Klein, which is odd under inversion. That's why it has to be L equals 15. That was the argument. It's not that they just did fitting. There was a good reason just to take L equals 15. And so they concluded the smallest viral capsid must correspond to L equals 15. There's a left-handed and a right-handed version, presumably corresponding to left-handed and right-handed amino acids. So it's a beautiful idea, actually. And what is remarkable, the Q15M he found simply from the kind of tables which Felix Klein wrote down. You can extract them with group theory methods. So you don't even have to minimize a big Lambda free energy. Just by the power of mathematics, you can find the Q15M. That's great. Except you have to write down a proportionality factor, because the density is proportional to an icosahedral spherical harmonic for L equals 15. To get that, you still have to write down a lambda free energy. Remember, it's rho squared, rho cubed, rho to the fourth. If you stick this in here, then the cubic term goes away. Why is that? Because this is odd. And because this is odd under inversion, it integrates to 0. So there's no cubic term. So we have a quadratic and a quartic term. So, following Rochal and Lorman, we now should have a phase transition where we change R15, and we should see this amplitude going from 0 to a finite value. And it will be very important that there's no cubic term. If you now do that, if you take R15 positive, it's curving like that, and R15 is negative, then it first goes down, and then it goes up. So as you change R15, then exactly at R15 equals 0, two minima appear, minus R0 and plus R0, where this is just square root of minus R15 over 2u. This is a classical second order phase transition. The two states are exactly the two chiral partners which came out of the group theory for L equals 15. So they came up with the following prediction. Viral assembly should be a continuous transition. Okay. And it corresponds to spontaneous chiral symmetry breaking. They didn't emphasize that, but that is what the theory contains. So questions is this ordering transition purely second order because of chirality? So I was skeptical, because if you take chiral materials in 3 dimensions or in 2 dimensions, it's a first order transition. So it seemed to me strange that it becomes continuous if you put it on the surface of a sphere. Spontaneous chiral symmetry breaking is suspicious too, because these proteins are already chiral. So you shouldn't have a spontaneous chiral symmetry breaking. So there are some questions. So we decided to check. The first one is this quantity which was constructed by Lorman and Rochal really the minimum free energy? So we took laboriously this fourth order term, here it is, 15, 15, 15, M1, M2, M3, M4, a vast amount of computational work, and we minimized it, and we asked, is YH15, the icosahedral spherical harmonic, really a minimum? The first question is it an extremum? And we tested, yes, icosahedral spherical harmonic is an extremum. The next one is it's stable. Stability means that if you take the matrix of second derivatives, then it should have no eigenvalues. Turns out L equals 15 has either 3 or 3 plus 4 equals 7 negative eigenvalues. This is an enormous amount of work by my brilliant postdoc, Sanjay Dharmavaram. We checked back with L equals 6 to see if Paul Steiner didn't make a mistake, and he didn't. It has only positive eigenvalues, apart from the 3 zeros from rotations. So L equals 6 is very, very, very different from L equals 15. There doesn't seem to be a stable icosahedral state in the L equals 15 sector. This is how the lowest free energy looks like in the L equals 15 sector. It has only one 5-fold symmetry axis, and it belongs to the symmetry group D5. So, we have a problem. All odd icosahedral spherical harmonics turn out to be unstable. All of them, not only 15, but all the higher ones as well. We checked until we were blue in the face. There are stable ones, but they're even, 6, 10, 12, and 18, they're achiral. And Lorman and Rochal told us we need to exclude them because they're even. So we have proven by the power of pure reason that there's no such thing as icosahedral viruses, right? It's an absolutely watertight proof. They should not exist. At least they shouldn't exist as a single L Landau theory. It's just not possible. We've ruled out, yes?
Is only captured enough to have the chiral Casper plug, the LM?
The you're talking about the T+7 structure. So yes, there are chiral icosahedral structures. And they correspond to higher spherical harmonics, not L equals 15. So the Casper-Klug structures with T+7, which are intrinsically chiral, they would correspond to an odd L icosahedral spherical harmonic, but it wouldn't be stable. So there is something very strange. And after a lot of discussion, we decided to see what would happen if we relax the Landau rule. That is, if we don't assume that it's just a single dominant L. For that, I have to be a little technical. We used a variant of Landau theory called Landau-Brzozowski, where you have the same expansion you saw before, but now I assume that there are also gradient terms, and these gradient terms were set up by Brzozowski so that you get density waves with wave vector Q0. So if you put in here rho of r equal to I Q0r, then you see that this cancels that. So this is minimized by a wave. So the idea is you represent the surface by a set of waves which have roughly the wavelength of a viral protein, and you then ask yourself, what is the lowest free energy state? This doesn't, the advantage of doing that is you don't select any particular L ahead of time. So this Q0 is 2 pi over the molecular size, the size of one capsid protein. So if you have a flat surface, then this turns out the lowest energy structure. It's 6 waves along the x, along the z direction and along 2 directions, which make a 120-degree angle. If you superimpose these 3 density waves, you get a beautiful hexagonal structure. The k, you take here a unit vector along this direction, and you call this a star. So if you work it out, you'll find competition between hexagonal phases, lamellar phases, and all the symmetry with a beautiful complex phase diagram, which was worked out by Ludwig Leibler. So it's a very powerful tool to study competing phases. So we use this, and we inserted now in this Brzozowski free energy the expansion, which I've been using now so often that you must be sick of it. We put it in, and what you get is something which looks very similar to Steinhardt's term, except we have a sum over all L here, and no restriction anymore to one particular L in the cubic and in the quartic terms. So you have a sum over all L, and the Landau-Brozovsky theory tells us what the R sub L is. And do you remember, we are supposed to choose the L for which the R sub L was as low as possible. So that is now part of the minimization. The selection of L becomes, and it's no longer something by hand, you can do it because you have an explicit expression. And this explicit expression is that R sub L is this old constant R, and this is a new term which comes from Brozovsky. L times L plus 1 minus Q0 R squared squared. So here's how it looks like. You put in, for instance, L equals 15, you get a parabola as a function of Q0R. You put in L equals 16, you get another parabola. So over here, L equals 15 would be the best choice. Over here, L equals 16 would be the best choice. The reason for the appearance of this term comes from here. You might remember that if you work with a Laplace operator on a spherical harmonic, you generate L times L plus 1 over R squared. So the combination of these two terms after multiplication gives you exactly this term. So you see that all of these are sort of, they're not really parabola, they're quartic, but each of them has a minimum at Q0R. So by varying R for fixed Q0, I'll scan different L's. So this theory will tell me which L comes out. So as a function of Q0R, there's a region where L equals 15 and a region of L equals 16. There is an icosahedral state, but we saw it's unstable. So the idea is, well, what if we look at this multi-critical point here, right in the crossover, where Q0R is 16. At this point, where L equals 15 can compete with L equals 16. That's a huge problem in terms of numerical analysis. You have a space of 64 dimensions. L equals 15 is 31, and L equals 16 is 33, to L plus 1. So it's a 64-dimensional space that you have to minimize. Computers are powerful, and I'll tell you the result. I hope I'm not going over time. No. Here's the R, which you change. Here's the Q0R, our second parameter, which is the L selector. Remember, Q0R selects what value of L. Over here, you want to choose L equals 15, and over here, L equals 16. This is a non-icosahedral state, and this is a non-icosahedral state. But if you cool through this point, you get a second-order transition, and you get a mixture of stable L equals 15 plus 16. So if you're more on this side, it's more L equals 15. It's more on this side, it's L equals 16. And it is thermodynamically stable. All eigenvalues are either the three zeros or positive. So it is the interference between these two structures which has stabilized them. They don't exist as L equals 15 or L equals 16. They only exist as a superposition of different L. The Leibniz group theory, you need multiple irreducible representations to represent this state. It doesn't exist as a single irreducible representation. So this is different. And at this point, you get a phone call from the past, and you get some very negative feedback. We broke rule number 4. This breaks Landau's rule. Landau allowed different L, but only as entrained terms. He simply forbid this kind of thing to happen. This actually belongs, has something to do with something called a tetracritical point. I don't want to bore you with it. But here you have a second order transition which doesn't fit into any single L Landau theory. By the way, do you remember that Rochal and Lorman said it should be a second order transition? Lo and behold, we have a second order transition. I don't know where it comes from. I can't explain it. It's purely a numerical study. I don't have any idea how you get a mutual stabilization of 15 plus 16. I have no idea how, despite the presence of cubic terms, this seems to be a second order transition. I don't understand it, but this came out of the study. So I call it a tetracritical point. I didn't do that myself. Tom Lubensky saw it and said, oh, it's a tetracritical point. I don't really know what the tetracritical point is. So we still have the problem of spontaneous chiral symmetry breaking. There we are helped by the work of Pierre-Gilles Lejeune, who showed us how you really have to put in chirality. You start with an achiral Landau term, and you have the lowest order chiral pseudoscalar. So you need to take the Brozovsky theory and construct, these are all scalars under rotation and inversion. You need to have a term which is a pseudoscalar, and Sanjay, the same postdoc, constructed it. It's a monster. It's a first order term, but this is a pseudoscalar which is non-zero. I will not tell you the details, but it resolves all our problems. For the odd L icosahedral state, it removes the symmetry breaking, chiral symmetry breaking transition. For the even L now become weakly chiral, particularly because of thermal fluctuations. So if I add the chirality in the way of the Gen, namely by adding a pseudoscalar, all the difficulties seem to disappear. And the L equals 6, 10, and 12 states, which were stable, actually become weakly chiral. So we disagree with Lorman and Rochal, mainly with their insistence on throwing away the even L's. You can't. If you have a fully constructed Landau free energy, these 6, 10, and 12 are not achiral, they are only weakly chiral. So in conclusion, the Landau theory has two completely separate modes of viral assembly. One is with these intrinsically chiral shells, L equals 15 plus 16, via this tetracritical point with a continuous or weakly first order transition. And the opposite case is these 6, 10, and 12 states, which are weakly chiral and who have strongly first order transitions. They look very similar to the nematic transition I started out with. The cubic term is non-zero, it's a robust, strong first order transition. Viral assembly, I think, is a fantastic lab for testing Landau's rule. I will skip that. This is the group which did all the work. Sanjay Dharmavaram did all the hard math together with Joe Rudnick. This is Emmy, the one-eyed Chihuahua. These are all the other members of my group. These are the experimentalists who did the hard work. Bill Gelbart, Lise Garman, who's in Harvard right now, and Chuck Nobler. I want to finish by just briefly mentioning Vladimir Lorman. He passed away last year, and you might have the idea that I'm here telling you all his work is garbage. Absolutely not. He extended the concept, and what we did was just putting in the little bits to make it, to see that it's actually mathematically consistent. That doesn't mean it is right, but it is a mathematically consistent idea to take a Landau theory and apply it to viruses. I don't know if it works. Experimentalists will have to tell you. So the fact that we had to go through all of this mathematical analysis is simply you build it up. But it was his idea. So the fact, if a person has a great idea and there are little things which have to be fixed up, that's part of the normal process of science. And it doesn't mean that because his idea was not complete at the start, he shouldn't get the credit. So if this idea turns out to be right, Lorman deserves all the credit. And thank you very much. And, I didn't go over time. Acidity and salinity.
Right. So I mean, people measure how ordering was when you change this.
So the French experiment, which I went through quickly, using thermal shift fluorescence assay, and I know nothing about it, claims it's a first order transition. That's all I can tell you.
And the knob in that case is the acidity?
I do not know. I simply, it's a good question. I didn't read the paper carefully enough what the knob was, what they were using. I particularly like the experiment done by my colleagues in UCLA because it could be done reversibly. They can very slowly change the acidity and see very carefully to the assembly. Of course, you can put it all in the tube and shake it and it may come out. But in order to measure, to test, for example, the order of the transition, you need this controlled experiment. Most other cases, it's not controlled. And there is another mode for assembly where you imagine that you form kind of a bowl which grows, and the RNA is sucked in. Numerical simulations by Michael Hagan from Brandeis have shown that you can have both modes. This kind of collective mode of assembly where you start with kind of block which then solidifies. And the other one is that you form a growing shell, like in crystal growth, and the RNA gets sucked in. And it depends which is the stronger interaction. is the strongest interaction protein-protein, or is the strongest interaction protein to RNA? And you can change these with salt and salinity, but they are very tedious experiments because you can't look at them. Viruses are much smaller than the wavelength of light. So after every experiment, you tediously have to do cryo-EM, so it is a big mess. Yeah.
Okay, so Robin, this is absolutely beautiful, so I want to break it.
Other question, please.
But I'm imagining that you make the RNA much bigger, so that it takes a lot more capsid proteins. So that means that you'd have to have a larger L, I would assume, solution. So there must be a hierarchy of these solutions.
Absolutely.
Is there a top to that hierarchy?
Is there a top?
Is like you get it big enough so that this doesn't work anymore and the thing gets all fluffy and falls apart?
So it is certainly true that if you make larger viruses, they're more floppy. And typically what happens is, let's take the one I know a little bit about is the herpes virus, which is much larger than this. The way they assemble, you probably would have guessed, they assemble on a scaffold. They take first one kind of protein, which forms a block at roughly the right size, and then they condense on top of that, and then the interior is dissolved, sort of what people do with nanofabrication. So if you have a very big virus, you tend to build it up on a pre-existing scaffold. Here is the RNA, which is the scaffold to some extent. So is that answering your question?
I think it does. It's a start. I mean, so you found the L equals 15 to L equals 16. That superposition seems to be magical.
Yes.
Is there another higher order island?
I may remind you, you're not a theorist, and I'm not an experimentalist. So this was a heroic achievement, diagonalizing 64 by 64 dimensional matrices and searching in a 64 dimensional space. There is, at this moment, we don't have the numerical tools to go to larger L. We just could do this for L equals 15 and 16, and we find this strange, this interesting result, this critical point in this superposition. Almost surely there's all kinds of interesting things. So let me show you one thing. Instead of going to bigger L, you can also go to smaller L here. So I call this an imaginary liquid crystal, which is L equals 5. That should be much easier, right? So if you take L equals 5, which is much easier to do on the computer, you find a very strange result. If you take the Landau energy, it's degenerate ground state. So these are all states which are degenerate with each other. It could be any of them. So this is not a disordered state. It still has an axis, the red line which you see here, the red line, but it has a continuous set of ground states. So I'm convinced that in this hierarchy of different L's, there are all kinds of mathematical treasures. L equals 5. I don't know any liquid crystal which corresponds to L equals 5. But if you find one, you'll get the Nobel Prize. I think.
Or at least the person.
What? Yeah.
In the functional with the gradient test that you used in the end, Landau somebody? Brzozowski, sorry. So you had four derivatives, right?
Yes.
So that means there is some state with k to the 4th in dispersion relation. And where is
yes.
So
Do you remember that? Do you remember that I showed you this R sub L? Sorry, it takes me quick. There we are. Here, do you see here Q0 squared? That's the Q to the 4th. So when you insert this into the Landau-Brzozowski theory, you get forced derivatives. That is reflected in that dependence of here. But is that what you were asking?
No, I'm asking why that input. I mean, if I just wrote the functional,
yeah.
Landau-Brzozowski functional, there you write already from the beginning Laplacian squared, Laplacian plus Q squared squared.
Yeah, that's right.
Which is four derivatives.
That's right.
So you could have written term with lower derivatives.
Okay. So the Landau-Brzozowski theory was worked out to have a theory which would have as its ground state waves. So we wanted to have they wrote down this term so that plane waves would be, that's zero of that term.
But I could have
You could have other terms. You can put it, for instance, you could take the same term to the second. You can take it to higher power.
Rho times Laplacian plus q square rho. In the equation of motion, that still will give
Okay,
you
so-
the solution.
You will. I challenge you. If you just have gradient square term, you will not get a term for which the wave vector minimizes q equals q0. Try it. You get q squared. You have a linear term, right?
I have rho Laplacian plus q square rho. If I vary that, that's Laplacian
Let's
plus
talk
q
after
square
that.
plus rho, and that is a solution.
I need a blackboard. Let's talk afterwards. Okay. More questions?
I have actually a question to you, Robin.
A joke or a question? Okay.
Sure, absolutely serious.
All right.
No jokes. About this argument that chiral proteins imply sort of chiral structure, and then you need odd spherical harmonics. Why is it? Why this argument in the first place? The fact that intrinsically these proteins are chiral does not mean that they assemble in a chiral way.
Yep.
It's not necessary.
Yep.
For instance, the fact that our proteins are chiral, the fact does not imply that my right hand and left hand are necessarily different.
Okay. Let me show you the slide. So, it's just making your point. Let's look at an L equals 6 state. So, should we reject that to make a virus? Well, there's no reason to reject it, because here's an example from nature. It's called the picorna virus, and it's assembled from highly chiral units, these ones. They are composed of 15 proteins, and you can see the chirality. It's twisting around a lot. But nothing stops you. What?
They are like propellers.
They're like propellers. But nothing stops you from taking the center of mass of... These ones exist in solution before you assemble it. They exist as pentamers floating around. Nothing stops you from assembling these ones where the center of mass of each of them is located around one of these red spots. And they don't have to be chiral. In other words, you can it's just your point. You can take an achiral lattice and put chiral objects on that lattice, and there's nothing wrong with that. You can do it with a crystal. You can take a perfectly cubic. So I agree with you, and I don't think that Lorman's argument was compelling. That's why I think you have to include L equals 6, 10, and 12. Simply you have to accept that you're going to put chiral objects on there. It turns out, if you're looking at thermal fluctuations, when these things begin thermally fluctuating, then it turns out that they show up. But they don't show up in the zero temperature structure.
Any other questions? No other questions? Then everybody knows where to go. That's